Hello everyone, welcome to the P1 program. This lecture is called P104.1. In this lecture, we are going to handle the vectors and scalars and Cartesian and coordinate systems. Okay, so first of all, what is a vector and what is a scalar? If you say that you are going out of your home to buy something, you go from point A to point B, and that's the direction that you're traveling. If it's a straight path, you take the shortest path and you get something like 40 meters, okay, distance. Now if you are having a curved path, like you have to go all the way around to get to the shop, that means that path might take 80 meters, twice the distance. Now these two paths are different, right? The first path had a specific direction and it was going in a straight line. That path is called the shortest path, and that path you can call it as displacement. And the longest path, which was a curved path, which had no direction, but it was constantly changing its direction. As you can clearly see, there is constant change in direction, and this path is called distance. So here distance is a scalar and displacement is a vector. The intrinsic property that you can see here is that the distance has no direction, particular direction, but displacement has a direction, right? Displacement will always has a direction. Now how can you represent this kind of a motion? If you want to tell your friend that when you travel from your home to the grocery shop, and your friend calls and asks you where you are, and you are going to tell him that you are 40 meters away from your home, but that doesn't mean anything, because the 40-meter can be a perfect circle from your home, and so the grocery shop can be in any direction, right? It could be anywhere in this circle. It's a perfect circle, but I drew it like this. Sorry about that. But that's what's going to happen when you communicate with someone and say that you are 40 meters away from your home. So you cannot specify, you cannot pinpoint. So for pinpointing, you can add some value. You can say that your home, you are northeast, northeast, 40 meters northeast to your home. Even then, that is a part of a quadrant, right? So it's northeast. With northeast, you are restricting yourself with a quadrant, in the first quadrant, and you're saying that you are somewhere in here. So you could be anywhere in here, 40 meters anywhere away from here. So that itself is not absolutely precise. So you want to have a precise system that represents your position. So you can break up, you can say you can have a vertical line and a horizontal line, and you can break things up in two dimensions. You can break things up into unit spaces. So you can call this 0, and you can call this 1 in the x direction, and you can call this 1 in the y direction. Now if you want to represent something here, you can just say it is 1 in the y direction, and it is 3 in the x direction. So it's 3 1 in x and y, right? That's the basic representation. Now you can draw from the center, you can draw a line to that point, and you can say that you can represent this in another form. You can say you're 3 times unit x plus 1 times unit y. So unit y and unit x is usually represented as x cap and y cap to represent unit numbers. It's a unit vector. So you clearly have a representation. This kind of a representation is called vector representation. So your position equation has now become 3x cap plus 1y cap. So that's the position vector. Now you can add anything to it. You say you want to represent something that is twice as far from here. You can say you can multiply it with 2 and you get 6x cap plus 2y cap, right? So you can do anything with this vector, and you can add the components itself, right? Now looking at a different thing, you and your friend are chained together with a rope, and you want to go in this direction, and your friend want to go in this direction. What happens is that uh, when you move in this direction, your friend will find himself pulled onto your side by the force of your which you are moving, and also your friend, when he moves to this direction, will pull you backwards. So your motion is not going to be precise as you have intended. It will be deviating, right? These vectors can be represented, right? If you are looking at some motion like this and some motion like this, when you both are pulling onto each other, your combined body will move in a direction that is something like this. So this is called a resultant vector. Now how can you introduce a resultant vector? Well, to find resultant vector, you add two vectors. Say you add two vectors to find the resultant vector. That's how you get a resultant vector. Now how can you do that? Let's bring in the coordinate system. This is the coordinate system. Let's say this be the coordinate system, and you have the first vector here and the second vector here. First vector is called P and second vector is called K. So it has an x-intercept. K has an x-intercept, which is the value of x component, which is kx, and it has a y-intercept, which is ky, and P also has an x-intercept, which is called px, and y-intercept called py and px, right? When you add these two vectors, I'm going to redraw this because it was so small. When you add these two vectors, right? When you add these two vectors, you will find that the shortest, when you add them, then the excess must be added on to this side, right? And you will get a new point. And similarly, the excess here from here will be added on to this side, and you get a new point. So these new points will connect with each other and you get a resultant vector. That's how you get a resultant vector. Okay, this vector, the magnitude will be say p plus k. That's the vector right there. So how can you numerically do that? You say px x cap plus py y cap, and kx x cap plus ky y cap can be added together by just adding the components of x intercepts and y intercepts. So you can just write it like that, and you get your new vector, which is p plus k. You can call it c. So c is equal to this vector is represented here. Okay, so that's how you add two vectors. Okay, we have discussed three-dimensional, two-dimensional cases here. So looking at three dimensions, you can see that when you have x and y in this axis, you can add another dimension, which is z, and you can now say that all the real things in your world, in our world, is actually in three dimensions. So you have to represent a vector in terms of 3D. So this is the vector here in 3D vector, and it will have an x-intercept, a y-intercept, and also an z-intercept, right? So you can write down the vector now as in the case of p of x and y and z as px of x cap plus py of y cap plus pz of z cap. So that's how you represent the vector in three dimensions. If it was a distance, as we have mentioned earlier, if it was the distance from your home to the grocery store in three dimensions or whatever, then you would have to find out the distance, right? So distance was 40 meters. So how do you represent 40 meters in this set of equations? You can just say that 40 meters is the magnitude of this vector, and that magnitude can be represented as p, which is equal to square root of px square plus py square plus pz square, right? That's how we represent it. Now where did it come from? So if you look at a two-dimensional vector, you can see that this was the vector, and it has a px intercept and this has the y intercept. So you can just basically say that this value will be also be y, and this value will also be x. That means using Pythagoras theorem itself, you can say that this value of p will be square root of x square plus y square, right? So that's when you add another dimension to it, you get z square as well. So that's how you represent the magnitude. As for example, you have a vector, say p is equal to 3 times x cap plus 2 times y cap plus 4 times c cap. You can say the magnitude of p will be equal to square root of 9 plus 4 plus 16. So that's equal to square root of 29. So that's a basic distance, right? It will be around say 5.4 or 5 or something like that. So it will be around that, approximately around that. So that's how you represent a vector. That's how you find the magnitude. That's how you represent vector, and that's how you introduce vectors into the system. Now also along with that, if you want to say add, say you have a vector like this and you need to you can do all other things with this vector. You can say you can multiply it with 2 and you get twice the length and the same direction. If you multiply it with -1, you get something like this, and it will cancel each other and it will be a null vector. It will be a 0. It has no direction because the direction is cancelled by the vector having the same magnitude but a different direction. So similarly, you can, if you have a vector p, then you can multiply it with c and you get every component multiplied with c. Okay, so that's how vector multiplication works, and we will introduce much more things later. And you can also add two vectors. I have showed you how, and you can also introduce other factors as well. You can divide, you can add a minus sign and reverse the vector itself. If it was p here, if you multiply it with minus c, right, see, if it's c is equal to 1, then you get a vector which is in the opposite direction, in the same magnitude but in the opposite direction. So that's how vector products and vector spaces works. Okay, so with that, I'm going to close in the first part.